Okay, so we're continuing on with chapter 5, which focuses on chemical equations and stoichiometry. We previously discussed many methods for balancing chemical equations, and now we're putting those methods into practice using a series of examples. So to help us get back in the rhythm of things and to help us refresh how to balance chemical equations, I'll be doing this representative example, and then you'll focus on the next example on this page. So we're asked to balance the following chemical equation, and any method can be used. Okay. So this equation looks a little bit complicated at first glance, but if we focus on the elements that are found in the least number of compounds, we can balance this equation quite efficiently. So in terms of our counts, on our reactant side, we have, looking at our hydrogens, we have 3 hydrogens, 1 phosphorus, and 4 oxygens. In barium hydroxide, we have 1 barium atom. Remember, the subscript applies to everything in the parentheses, so we have 2 oxygens and 2 hydrogens. In barium phosphate, we have 3 bariums, 2 phosphorus, and 8 oxygen. And in water, we have 2 hydrogen and 1 oxygen. We're going to leave oxygen alone for now because it's present in a large number of different compounds and as a result would be quite challenging to balance normally. However, we do have a pretty easy target to balance because phosphorus and barium are found in only 1 compound on each side of our chemical equation. So, using our coefficient method, if our end goal is to end up with 3 bariums, what coefficient do we need in front of barium hydroxide? 1 times what would give us 3? 3, yep, exactly right. So that gives us 3 barium, 6 oxygen, and 6 hydrogen. Likewise, for phosphorus, if we have 2 phosphorus on the right and 1 phosphorus on the left, 1 times what would give us 2 phosphorus? 2, exactly right. So we plug in our coefficients. That gives us a revised count of 2 phosphorus, 6 hydrogen, and 8 oxygen. So we're going to look at our totals. We're going to look at our totals for a moment. And looking at our totals for the following chemical equation, we see that in total, we have 12 hydrogen and 14 oxygen. We're going to keep this in mind because in barium phosphate, we have 8 oxygens, and in water, we have 2 hydrogen and 1 oxygen. Let's focus on balancing hydrogen now. So in terms of our counts, 2 times what would give us 12 hydrogens? What coefficient do we need for water now? What coefficient do we need for water now? 2 times what would give us 12?
6.
Exactly right. 2 times 6 gives us 12. So we have 12 hydrogens and 6 oxygens. Combined with the 8 oxygens that we already have gives us 14 oxygens total. So hydrogen and oxygen are balanced. So then we can now introduce our coefficient, and we now have a complete and balanced chemical equation. Does this question make sense to everyone? Any questions on this example? Okay, so let's apply what we've learned to the following example. We're looking at an acid-base and decomposition reaction involving hydrochloric acid and lead carbonate. So I'd like you to take a moment and I'd like you to try and balance the following chemical equation. And I'd like to see your work in balancing the chemical equation. If you could show the atom counts or what method that you're utilizing, that'll be extremely instructive in helping us highlight important aspects of each problem-solving method and discussing discussing any potential student responses that we have for balancing the following chemical equation. So let's take about 3 to 4 minutes to work through this example, and then we'll come together as a group to discuss. So let's try to balance the following chemical equation. And I'd like to see students share their responses or questions using the annotate feature or in the chat. And if you're ever stuck on any part in balancing this equation, make sure that you can always ask a question in the chat or verbally.
Professor, can you scroll up real quick to the previous
Sure.
example?
One moment.
Just for a quick second.
No,
Thank
of
you.
course, of course.
Professor, I have a question on that one that you're scrolling
Yes, please go ahead.
down on.
Mhm.
The 80 plus 12 hydrogen and 6 oxygen, you're saying it equals 140 or 14?
So the O's aren't zeros, they're representing oxygen atoms. So for example, showing this count, we put a 6 in front of water. So that in turn gave us 12 hydrogens and 6 oxygens. That's where this first 6 is coming from.
Mhm.
The reason why the 12 hydrogens are important is because it matches the 12 hydrogens on the left-hand side. Does that make sense?
Yes.
So since we already have 8 oxygens to begin with from our barium phosphate, if we add up 8 and 6, that gives us 14 oxygens total, which matches the 14 oxygens found on the left-hand side.
Right. Okay. I was just wondering.
Does that make sense?
Yes.
So
yes, thank you.
if one way to help organize things is you could even potentially just underline the element symbols, just so that way it's completely unambiguous which symbols are representing numbers and which symbols are representing letters.
Okay, I get it
Does that
now.
make sense?
Thank you. Yes.
Perfect. I know for oxygen, I also get caught up sometimes if I'm looking at oxygen, wondering whether it's an oxygen symbol or a 0. Okay.
Okay, got it.
So let's take a look at the following example. Let's try to balance the following chemical equation. And then from there, let's try to share our balance coefficients in the chat or verbally. And we'll discuss this example in about another 4 to 5 minutes. And of course, if you have any questions, don't be shy to ask them verbally or in the chat. You can also use the annotate feature to write on our class whiteboard and share your proposed responses on the class whiteboard. And we'll discuss this example in about 4 to 5 minutes. And it's great to see that students are already contributing their responses for this balanced equation. Let's keep working through this example and then we'll discuss. And it's great to see students are contributing their responses. And just to convey the common student responses that I've seen so far, students are proposing the following set of coefficients for this balanced equation. And as you work through this example, don't be shy to comment whether you agree or disagree with these proposed balanced equation coefficient? And we'll discuss this example in about another 2 minutes. It's great to see that we have multiple responses in the chat. I just wanted to give a few other students some additional time to balance the following equation before we discuss. Okay, so let's discuss this example. So the proposed balanced equation coefficients brought forth by many members of our class have been exactly perfect. So let's discuss the logic behind it. How do they reach this conclusion? Well, first, starting our preliminary counts, we have 1 hydrogen and 1 chlorine and hydrochloric acid. In lead carbonate, we have 1 lead, 2 carbon, and 6 oxygen. In water, we have 2 hydrogen and 1 oxygen. In carbon dioxide, we have 1 carbon and 2 oxygen. And in lead chloride, we have 1 lead and 4 chlorine. Okay, so let's pick the element that is found in the least number of compounds. So let's balance chlorine. So 1 times what would give us 4 chlorines? 1 times what would give us 4 chlorines? What coefficient do we need?
4.
Exactly right. That in turn gives us 4 chlorine and 4 hydrogen. Okay. So we've sort of created an issue with hydrogen now, but we can just as easily balance it. So if we want out 4 hydrogens in the end, 2 times what would give us 4? 2 times what would give us 4? 2, yep. So with a coefficient of 2 for water, we get 4 hydrogen and 2 oxygen. Now looking at carbon dioxide, we see we have 2 carbons on the left. We have 1 carbon on the right. So 1 times what would give us 2 carbons? What coefficient do we need for carbon dioxide? 2, exactly right. So that gives us 2 carbons and 4 oxygens. Okay, so in total, we have 6 oxygens on the right-hand side, which matches the 6 oxygens on the left. So we have hydrogen, chlorine, lead, carbon, and oxygen all balanced. So we have our complete balanced equation with the correct coefficients. Does that make sense to everyone? Any questions on this example? Okay, so let's keep going now. And let's talk about how we apply our balanced chemical equation? What can we do with our balanced chemical equation, and why is it so important to have a balanced chemical equation? Well, stoichiometry is this idea that chemical reactions require a specific whole number ratio of reactants for a complete reaction. Likewise, a whole number amount of product molecules are produced based on the chemical equation. We have intuitive experience with this idea. So for example, if you ever try to make a sandwich, for example, we can draw a picture of this to help us visualize what's going on. Your recipe for a sandwich can involve 2 pieces of bread and 3 pieces of cheese, okay? So in our chemical equation map, we have 2 pieces of bread. We need 3 pieces of cheese to finish off our sandwich. And in the end, if we take our 2 pieces of bread and 3 pieces of cheese, we get out 1 sandwich, right? We start with a defined number of each reactant based on our recipe, based on our chemical equation, and we get out a defined number of products. So from our chemical equation, we can figure out the amount of each reactant that we need and each product that we make. Okay, so let's try to answer some questions where we analyze this quote unquote chemical equation. So let's suppose we have 2 pieces of bread. So we have 2 pieces of bread. How many pieces of cheese do we need? How many pieces of cheese do we need?
3.
3. Yeah, looking at our recipe, we need 3 cheese. So in other words, we can write this as a conversion factor. So we need 3 pieces of cheese for every 2 pieces of bread. This, in turn, is a conversion factor. So from our chemical equation, we can make a series of conversion factors. We have a relationship in our chemical equation between the amount of each reactant required. Likewise, for every 2 pieces of bread, how many sandwiches do we make? So how many sandwiches do we make? And exactly right. We get 1 sandwich out per every 2 pieces of bread. From our picture, from our recipe, we see if we put 2 pieces of bread in, we get 1 sandwich out. Again, we have another conversion factor to utilize. Finally, if we have 3 pieces of cheese, how many sandwiches do we make?
1.
1, exactly right. We get out 1 sandwich per every 3 pieces of cheese. So as we've noticed, just like in a formula ratio, we have generated a conversion factor based on our chemical equation. And we call this conversion factor, it has a very fancy name, a stoichiometric ratio. And it provides a relationship between the amount of a reactant and a product in our chemical equation. Does this idea make sense? Does this analogy help you understand a little bit about how a chemical equation is utilized and how we can relate the amounts of each of our reactants and products? Does this analogy make sense to everyone? Okay. So now that we've seen an analogy, let's look at how we can utilize these stoichiometric ratios to perform calculations. Now, a chemical equation has a distinct ratio of reactants and products, and this ratio is based on our reaction coefficients. And we can use this stoichiometric ratio to perform calculations. So drawing out our picture for this chemical equation, we have 2 pieces of bread and 3 pieces of cheese. We mix them together, we get 1 sandwich. We can use this chemical equation to answer questions related to stoichiometry. So if you start with 4 pieces of bread, how many pieces of cheese do we need to completely use up all of our bread? So we want to go from our 4 pieces of bread and we want to convert it and figure out the number of cheese pieces that we need. As we notice, students are already intuitively noting that they would need 6 pieces of cheese. There are 2 ways of figuring that out. In the most straightforward way, you can draw out a picture and you see, so for every 2 pieces of bread that I draw, I need to draw 3 pieces of cheese. Okay? Since I ended up drawing out a total of 4 pieces of bread, I need to draw 6 pieces of cheese. Now, this is all fine and dandy when you have relatively small coefficients. This method can certainly allow you to relate the reactants and products for small coefficients. But what I'd want us to start to utilize is our conversion factor method. So just like any conversion, if we're going from bread to cheese, if we're going from one unit to another, we just need to find a conversion factor containing our desired unit on top and our starting unit on the bottom. So if we start with 4 pieces of bread, do we have a conversion factor? How many pieces of cheese do we need per how many pieces of bread? What is our quote unquote mole to mole ratio? What's our ratio of cheese to bread? Looking at our equation. What's our stoichiometric ratio? 3 to 2, exactly. We need 3 pieces of cheese per every 2 pieces of bread. So using our conversion factor, which is derived from our chemical equation, we see units of bread cancels and we're left with 6 pieces of cheese. This is the method that I would like you to use whenever you encounter a stoichiometry problem. You identify your starting and ending units, you look at your chemical equation and get a stoichiometric ratio that has your desired units on top, your starting units on bottom, and then you just multiply it out. Does this conversion factor method make sense? You've done this exact same process when you looked at a formula ratio. The only thing that's new is you're getting this ratio from your chemical equation. Does that idea make sense to everyone?
Professor, do we cross cancel the 4 and the 2 also, or just?
Yes. So the 4 and the 2 cancel, and that in turn gives us 2.
So that's what gives us the 6 cheese?
Yep, exactly, because 2 times 3 gives us 6.
Got it, thank you.
So by the same token, we can figure out, given the amount of reactants, how many products we get out. So if we start with 9 pieces of cheese, how many sandwiches would we make? Well, we can do this pictorially once again. So if we draw out our 9 pieces of cheese, let me draw it farther to the left so that way we have more space. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that we know for every 3 pieces of cheese, we can get out 1 sandwich. So for every 3 pieces of cheese, we can get out 1 sandwich. Okay? So intuitively, if we start with 9 pieces of cheese, we'd get out 3 sandwiches. However, we can solve this problem using our stoichiometric method. So we're trying to go from cheese to sandwiches. Okay, so if we start with 9 pieces of cheese, looking at our chemical equation now, how many sandwiches do we make per how many pieces of cheese? What is our stoichiometric ratio? What is
One
our,
sandwich per 3 cheeses.
yep, exactly right. And so now that we have our stoichiometric ratio set up, we multiply by our stoichiometric ratio, cheese cancels, the number 3 cancels, and we're left with 3 sandwiches produced. Does this idea make sense to everyone? Does this idea of reading the chemical equation to get a stoichiometric ratio make sense? Wonderful. Okay, so we're now going to apply this idea to a chemical equation. And before you panic, notice that the reaction coefficients are exactly identical for this chemical equation compared to our bread and cheese example. This iron can be thought of like the bread in our previous example. This chlorine can be thought of as the cheese in our previous example. And this iron chloride product is the sandwich that we are making. The exact species in our chemical equation are not as important as our reaction coefficients. So let's apply what we've learned in stoichiometry to the following chemical equation. So we're asked how many molecules of chlorine are required for complete reaction with 2 atoms of iron. So we're trying to go from atoms of iron to molecules of chlorine. Well, we know intuitively, looking at this chemical equation, if we draw out a picture, we have 2 atoms of iron reacting with 3 molecules of chlorine. And in the end, at the end of this reaction, we get out 1 molecule of the following iron chloride product. Okay, so then if we have 2 atoms of iron, looking at our pictorial representation, how many molecules of chlorine do we need to react with 3? Exactly right. It's a 2 to 3 ratio. We can also showcase this using our stoichiometric method. If we start with 2 atoms of iron, we're going from atoms of iron to molecules of chlorine. And now how many molecules of chlorine are required per how many atoms of iron? Okay, so how many molecules of chlorine do we have in our chemical equation ratio? What's our mole to mole ratio for chlorine to iron?
3 to 2.
Yep, so we need 3 chlorine molecules for every 2 atoms of iron. Atoms of iron cancel, the 2 cancels, and in turn, we're left with 3 chlorine molecules. Does this make sense to everyone? Does this idea make sense? Does everyone notice how this is exactly identical to the previous bread and cheese example? The only thing that we have changed, in this entire process is that we are now talking about species in a chemical equation. Does that make sense to everyone? Okay, so let's keep going with this idea. We're asked how many molecules of this iron chloride product are generated for every 2 atoms of iron that react. So we're going from 2 atoms of iron to molecules of this iron chloride product. So starting off with 2 atoms of iron, if we're trying to go from atoms of iron to molecules of iron chloride product, how many molecules of this iron chloride product do we make per how many atoms of iron? What is our stoichiometric ratio? 1 to 2, exactly right. We get 1 iron chloride product out per every 2 atoms of iron. Atoms of iron cancels, and in turn, we end up with 1 molecule of this iron chloride product. Does this make sense to everyone so far? Any questions so far? Okay, so to complete our list of stoichiometric ratios, we're asked how many molecules of this iron chloride product are produced for every 3 molecules of chlorine that react. So we're trying to go from 3 molecules of chlorine to the molecules of this iron chloride product. So starting off with 3 molecules of chlorine, how many molecules of this iron chloride product do we have per molecule of chlorine that react? What is our mole to mole ratio? Yep, we have 1 molecule of this iron chloride product produced per every 3 molecules of chlorine that react. And that in turn, at the end of our chemical equation, we see the molecules of chlorine cancels, this 3 cancels, and we're left with 1 molecule of this iron chloride product generated from our reaction. Does that idea make sense? So we've looked at all of our reactant to reactant and reactant to product stoichiometric ratios. Is everyone comfortable with this idea so far? The most important part in this entire process is being able to quickly generate a balanced chemical equation. And once you have your balanced equation, you can generate your stoichiometric ratio and use that ratio to convert between reactants and products. Does this idea make sense? Okay, so let's keep going now. And let's try to apply what we've learned to another stoichiometric ratio. This time we're asked to do a series of atom to molecule and molecule to molecule conversion. So if we start with 4 atoms of iron, how many molecules of chlorine are required? So in this case, we're asked to convert from atoms of iron to molecules of chlorine. So starting off with 4 atoms of iron, to complete our conversion, we're going to go from atoms of iron to molecules of chlorine. Molecules of chlorine is on top, while atoms of iron is on the bottom. So what is our mole to mole ratio? How many molecules of chlorine do we need per how many atoms of iron? Looking at our original chemical equation, what's the relationship between chlorine and iron? What's the relationship? 3 to 2. Exactly right. So we need 3 molecules of chlorine per every 2 atoms of iron. Atoms of iron cancels, the 2 cancels, and we are in turn left with 6 molecules of chlorine. Exactly identical to the bread and cheese example that we did earlier. Does this make sense to everyone so far? Does this idea make sense? Okay, let's do one more example, and this may feel like repetition because the stoichiometric coefficients and the amounts are exactly identical to the bread and cheese example that we covered. So we're asked how many molecules of this iron chloride product are produced when 9 molecules of chlorine react. So we're asked to convert between molecules of chlorine and molecules of this iron chloride product. So then, starting off with our 9 molecules of chlorine, if we're going from molecules of chlorine to molecules of this iron chloride product, how many molecules of this iron chloride product are produced per molecule of chlorine that react? What is our stoichiometric ratio? 1 to 3, exactly right. So we generate 1 molecule of iron chloride product per every 3 molecules of chlorine. Molecules of chlorine cancels, the 3 cancels, and we're left with 3 molecules of this iron chloride product. Does that idea make sense to everyone? Is everyone comfortable with this idea? Okay, so we can think of mole ratios in chemistry in 2 ways. We can look at an element or ion mole ratio, which relates the amount of moles of each element in a compound. So for example, in the following formula, so from this formula ratio, we see we have 4 moles of phosphorus for every 10 moles of oxygen in this compound. Likewise, we know that we have 4 moles of phosphorus for every 1 mole of P4O10. Again, both of these ratios are dependent on our chemical formula, and these 2 mole ratios are called formula ratios. We've seen these before in chapter 4 when we performed mole-to-mole conversions. So these types of mole ratios should be familiar to all of us. However, the new mole ratio that we're discussing in this chapter are our chemical equation mole ratios, also known as the stoichiometric mole ratios. So, chemical equations indicate the number of each reactant molecule consumed by a chemical reaction and the number of each product molecule produced by a chemical reaction. Now, from this, a chemical equation and the chemical equation reaction coefficients provides us the relationship between the moles of a reactant and the moles of a product or another reactant in our equation. So likewise, by reading off from our chemical equation the reaction coefficients, we can in turn generate a series of stoichiometric ratios. For example, for every 6 moles of water that react, we need 1 mole of P4O10. So this is our stoichiometric ratio. Likewise, for every 4 moles of phosphoric acid that we produce, we use up 6 moles of water. For our final stoichiometric ratio, for every 4 moles of phosphoric acid that we make, how many moles of P4O10 do we need to react? 1, exactly right. We're just reading off from our coefficients, remembering that a blank space refers to a coefficient of 1. Does this idea make sense?
Yes.
Perfect. So let's talk a little bit about mole ratios from a chemical equation and how to utilize mole ratios. So the chemical equation provides us a relationship between the moles of a reactant and product and the moles of one reactant in a chemical equation and a second reactant also participating in the chemical equation. So, for example, if we're given the phrase nitrogen and hydrogen gas react to yield ammonia, I'm immediately going to draw a picture. I find we can approach things intuitively if we have an accurate mental picture of what's actually going on in our chemical reaction. So we have one nitrogen molecule reacting with 3 hydrogen molecules to make 2 molecules of ammonia. This equation has already been pre-balanced for us, so we don't have to worry too much about that for now. Though keep in mind, we have all the tools at our disposal to balance these chemical equations with no issue. Okay. So now that we have our balanced equation and we've drawn a picture, we're asked how many moles of hydrogen are required to react with 6 moles of nitrogen. So we're converting from the moles of nitrogen to the moles of hydrogen. Okay, so starting with 6 moles of nitrogen, if we're going from moles of nitrogen to moles of hydrogen, how many moles of hydrogen do we need to react per how many moles of nitrogen? What is our
3 to 1.
Yep, 3 to 1. We see from our picture, we need 1 to 3 moles of hydrogen to react with 1 mole of nitrogen. Okay, so in turn, our moles of nitrogen cancels, and we're left with 18 moles of hydrogen. Does this example make sense to everyone? Perfect, perfect.
Professor,
let's-
where do you get the
yeah.
6 from for the moles of nitrogen?
Oh, that's just given in the problem for our starting amount. The initial input that you'll put into each of these stoichiometric
Oh, I'm
conversions-
sorry. Okay, yeah, I see it.
Does that make sense?
Yeah, sorry about that. Thank you.
No problem at all. Really don't be shy to ask a question. I'd be happy to answer it.
Thanks a bunch.
So likewise, in this example, we're asked how many moles of ammonia are produced when 3 moles of nitrogen reacts. So this is our input. So we're going to go from 3 moles of nitrogen to the moles of ammonia. So starting off with 3 moles of nitrogen, our question that we have to answer is how many mole, let me write this in a different color just to highlight how important it is. How many moles of ammonia do we make per mole of nitrogen that reacts? What is our mole to mole ratio?
2 to 1.
2 to 1. Looking at our chemical equation, we see that we get out 2 moles of ammonia per every 1 molecule of nitrogen that reacts. So as we see, the moles of nitrogen cancels, and we're left with 6 moles of ammonia. Does this make sense? Is everyone comfortable with this example?
Yes.
Perfect. So let's take a look at this next example where we're asked how many moles of hydrogen are required to produce 4 moles of ammonia. In this case, we're converting from 4 moles of ammonia to the moles of hydrogen. So starting off with 4 moles of ammonia, reading our chemical equation, how many moles of hydrogen are required per every mole of ammonia that is produced. So looking at our equation, what's the ratio between hydrogen and ammonia? 3 to 2. Exactly right. So we need 3 moles of hydrogen per 2 moles of ammonia, and that in turn gives us 6 moles of hydrogen. Does this example make sense to everyone? Is everyone comfortable with these examples? Okay, so let's keep going now, and let's have us apply what we've learned to the following example. So I'd like us to work on this following example, and I'd like us to complete the following set of stoichiometric conversions. So given the following chemical equation, I'd like you to tell me how many moles of oxygen are required to react with 5 moles of carbon monoxide, and how many moles of carbon dioxide are produced when 4 moles of oxygen react. So let's get started with these unit conversions, and then we will discuss in about 3 to 4 minutes.
Professor, can you have a half of a mole? Is that a thing?
Well, yes, because remember, moles are counting large numbers of atoms. So,
Oh, okay.
yes, so the number of moles doesn't need to be a whole number. The number of atoms or molecules does, because half an atom or half a molecule doesn't have any physical meaning. Does that make sense?
Yes, thank you.
Perfect. So let's keep working on these examples, and then we'll discuss in about another 2 to 3 minutes. So we're using the chemical equation to generate a series of conversion factors to convert between our starting units to reach our desired units. And it's great to see that we already are seeing some student responses in the chat. Let's keep working through these examples. And if you have any questions, don't be shy to ask your questions verbally or in the chat. And we'll discuss this example in another 2 minutes. Let's try to get a few more responses in the chat, and we'll discuss momentarily. And we'll discuss in another minute, but really don't be shy to share your questions and perspectives in the chat, and we'll discuss momentarily. Okay, so let's discuss. Let's discuss this example. So in this first case, we're asked to convert from the moles of carbon monoxide to the moles of oxygen. Okay, so we have 5 moles of carbon monoxide, and we're asked to figure out how many moles of oxygen are required. So looking at our equation, how many moles of oxygen are required to react with how many moles of carbon monoxide? What is the mole to mole ratio in our chemical equation?
1 to 2.
Yep, we need 1 mole of oxygen to react with every 2 moles of carbon monoxide. Our moles cancel. We're left with 2.5 moles of oxygen. Does this first part make sense? Does this first part make sense to everyone?
Yes.
Okay, so let's look at the second case. So we're asked to determine how many moles of carbon dioxide are produced when 4 moles of oxygen reacts. Okay, so we're asked to go from the moles of oxygen to the moles of carbon dioxide. So given 4 moles of oxygen, let's look at our equation and figure out our mole to mole ratio. So how many moles of carbon dioxide are produced per mole of oxygen consumed? What is our mole to mole ratio between carbon dioxide and oxygen? What's our mole to mole ratio? Would anyone like to volunteer? As we see in the chat, thank you. We have a mole to mole ratio of 2 to 1. We have 2 moles of carbon dioxide produced. Whoops, let me take a look just to make sure. Yep, 2 moles of carbon dioxide produced per every 1 mole of oxygen consumed, and that gives us 8 moles of carbon dioxide generated. Does this example make sense? Does this make sense to everyone so far? Okay, so let's look at another example. We're asked to figure out how many moles of carbon monoxide are required to produce 6 moles of carbon dioxide. So just to tie these examples together, we're trying to go from the moles of carbon dioxide to the moles of carbon monoxide. Starting off with 6 moles of carbon dioxide, we know from our chemical equation, looking at our chemical equation, the ratio between carbon monoxide and carbon dioxide is 2 to 2. Okay, so let's import that mole to mole ratio into this following problem. So we see that we need 2 moles of carbon monoxide for every 2 moles of carbon dioxide generated. That in turn gives us 6 moles of carbon monoxide for our final answer for this problem. We need 6 moles of carbon monoxide to completely react to make 6 moles of carbon dioxide. Do these examples make sense to everyone?
Professor, I have a quick question. Where did you get the 2 and 2 from the top?
Yes, so the coefficients are obtained from our chemical equation. So we see we need 2 moles of carbon monoxide to make 2 moles of carbon dioxide.
Okay, got it.
Does that make sense?
Thank you.
Perfect. So let's keep going and let's now talk about mass to mole conversions. So I provided this nice little chart that showcases all the relationships that we have developed so far in this class. The only thing that's new in our balanced equation is that it allows us to convert between the moles of one species in our chemical equation and another species in that same chemical equation. Now, once we have moles, we can just as easily go to grams and particles. To go to grams, we use our molar mass. To go to particles, we use Avogadro's number. And we'll learn in later chapters, we can go to volume using what is known as molarity. Okay, so once we have moles, we have a variety of tools at our disposal to convert those moles into other useful quantities like grams, atoms, molecules, etc. So when dealing with stoichiometry, the way that I like to approach these problems is following the following procedure, okay? First, we balance the chemical equation. That's the first thing you have to do always. Without a balanced equation, you can't do anything moving forward. You need a balanced equation to perform stoichiometric calculations. Next, you identify your starting units and your final desired units. To use your chemical equation, you need to be in units of moles. Now, as we've discussed previously, we can convert between mass and moles using the molar mass. You can convert between atoms or molecules and moles using Avogadro's number. You can figure out the moles of a specific atom in your molecule utilizing your formula ratio. And we'll save this discussion of molarity till next chapter, but you can convert between moles and volume in units of liters using the molarity of a solution. So once we have moles, we really have a range of options at our disposal. Okay. So with this scheme established, if we have moles, we can convert between the moles of reactants and other reactants and products using the chemical equation mole ratio. And we've done plenty of examples of that earlier on in this note set. So once we have our chemical equation mole ratio, we can go between the moles of our reactant and other reactants and products. And then once you have the moles of your desired chemical species, you can convert to your desired final units. I highly recommend that you write out the individual unit conversions needed, so that way you can check to make sure that the units cancel. So this is just a general scheme for solving these types of unit conversion problems. Let's showcase an example of this. Let's showcase an example of this process. Okay, so first let's just reiterate our simple mole to mole conversions. So we're given the following equation. This should look very similar to your previous example, but there's one key distinction that's important to avoid making a mistake on an exam. Can we use this equation as is right now? Can we use this equation as it's written currently?
No,
No. Why is that?
it's not balanced.
It's not balanced. Exactly right. It seems like such a subtle distinction, but it's really important. We need to have a balanced equation. So I'm going to balance this. I'm going to use the half notation method. I'm going to put a 1/2 in front of oxygen to balance oxygens. And then I'm going to multiply all my coefficients by 2. That gives us the following equation. Now that we have a balanced equation, we can move forward. Always make sure to check because most stoichiometry problems do not tell you whether or not an equation is balanced. They expect you to look at the equation and then figure that out. Does that make sense to everyone? Okay. This is like the number one way that students end up with problems when they do stoichiometry. Now that we have our balanced equation, we're doing the exact same process as before. So in this case, we're asked how many moles of oxygen are required to completely react with 5 moles of carbon monoxide. So we're going from the moles of carbon monoxide to the moles of oxygen. So given that we have 5.0 moles of carbon monoxide, let's look at our unit conversions. How many moles of oxygen do we need per mole of carbon monoxide? What's our mole to mole ratio? What's our mole to mole ratio?
It's 1 to 2.
1 to 2. We need 1 mole of oxygen per 2 mole of carbon monoxide. And always write your units. The more careful you are in writing your units, the less likely you are to make a mistake and flip the unit conversion factor. So as we see, moles of carbon monoxide cancels, and we're left with 2.5 moles of oxygen. Likewise, we can look at this next portion, and we're asked how many moles of carbon dioxide are produced by complete reaction of 3.5 moles of oxygen. Okay, in this case, we're asked to convert from the moles of oxygen to the moles of carbon dioxide. So if we have 3.5 moles of oxygen, how many moles of carbon dioxide do we make per mole of oxygen consumed? What is our mole to mole ratio relating carbon dioxide and oxygen?
3 to 2.
Wait, for carbon dioxide and oxygen?
Carbon dioxide, isn't it 3 to 2?
2 to 1.
Oh, so the coefficient for carbon dioxide is 2, and for oxygen it's 1. So it would be a 2 to 1 ratio. Does that make sense? So we read off the coefficient for carbon dioxide, which is 2, and the coefficient for oxygen, which is 1.
Oh, yes. Oh, okay. I'm sorry. Yes.
Oh, no problem. I just wanted to.
Yeah, I was looking at the wrong thing. Sorry.
Oh, no problem. No problem. Perfect. So we have our ratio of 2 to 1. We see the moles of oxygen cancels, and we're left with 7.0 moles of carbon dioxide. Following sig fig rules, 2 in, 2 out for multiplication. Does this idea make sense? Does this idea make sense? And the nice thing about this type of problem is we've already added a unique step. We've already added a step where we had to balance the equation. But as we notice, once we balance the equation, the final process is the same. We're just doing the same stoichiometric conversions. Any questions on this example?
Professor, how do you get 7.0?
So we take 3.5 and we multiply it by 2, and that gives us 7.
Got it. Thank you.
And the reason why it's 7.0 is because our input has 2 sig figs, our output should have 2.
Got it. Thank you.
Perfect. So let's look at another example. We've seen this equation before, but something's a little different about this equation. And So I'd like you to take a look at the following equation, and using this equation, I'm going to rewrite it down here. So using this equation, I'd like you to answer the following two questions. The first of which is how many moles of hydrogen are required to completely react with 2 moles of nitrogen? And then how many moles of ammonia are produced by complete reaction of 1.5 moles of hydrogen? So I'd like you to answer the following two questions, and then we'll discuss this example in about 5 minutes. And if you have any questions, don't be shy to ask in the chat or verbally. And don't be shy to submit your proposed responses verbally or in the chat, and we'll discuss in about another 5 minutes. And it's great to see we're already noticing student responses in the chat. Let's keep working on this example. And to help provide context, if someone would be able to share the balanced equation for this reaction, that would be extremely helpful in allowing students to help follow the thought process and work that students have utilized to solve this equation. So we have the student proposed balanced coefficients of 1, 3, and 2, and they use this balanced equation to complete the following two mole-to-mole conversions. So let's keep working on this example. Let's give students a little bit more time to compose their responses, and we'll discuss this example in about 2 minutes. Let's give students a little bit more time to submit their responses, and then we'll discuss in about another minute to a minute and a half. And it's great to see students submitting their responses and their proposed solutions to these problems. Okay, so let's take a look. So first things first, we need to balance the chemical equation. So just to showcase the logic behind balancing this chemical equation, we have 1 nitrogen and 3 hydrogen on the right. We have 2 nitrogens on the left. We put a 2 in front of ammonia. That gives us 2 nitrogens and 6 hydrogens. If we have 2 hydrogens on the left, we need a coefficient of 3 to end up with 6 hydrogens. So that gives us the following complete balanced equation, which we can now use for stoichiometry calculations. So in the first case, we're asked how many moles of hydrogen are required to completely react with 2 moles of nitrogen. Okay, so we're trying to go from the moles of nitrogen to the moles of hydrogen. So if we have 2.0 moles of nitrogen, looking at our stoichiometry, we see that we have 3 moles of hydrogen per every 1 mole of nitrogen. The moles of nitrogen cancels and we're left with 6.0 moles of hydrogen. Does this first example make sense? Okay. So then, let's look at the next part of this problem. In this case, we're asked how many moles of ammonia are produced by complete reaction of 1.5 moles of hydrogen. So in this case, we're going from moles of hydrogen to moles of ammonia. So if we start with 1.5 moles of hydrogen, in our conversion factor, we need moles of ammonia on top. So for our moles of ammonia per mole of hydrogen, we see that we have 2 moles of ammonia per every 3 moles of hydrogen. The 2 to 3 ratio comes from our stoichiometric coefficients. Punching in our stoichiometric ratio, we see moles of hydrogen cancels and we're left with 1.0 moles of ammonia. Does this example make sense? Perfect. So let's keep going now. And given a new chemical equation, I'd like you to balance the following chemical equation and then complete the following mole to mole conversions. The only thing that's new this time is that now we're asked to engage with a series of mass to mole conversions as well. So to showcase how to handle these sorts of multi-step stoichiometric conversions, let's start by looking at our equation. So as we see, we have 2 hydrogens and 1 sulfur, as well as 2 oxygens on the left, and we have 2 hydrogens, 1 sulfur, and 4 oxygens on the right. So then, in order to get 4 oxygens on each side, what coefficient do we need for oxygen? What coefficient do we need? 2. Yep, exactly right. Exactly right. Okay. Now that we have that set up, we're asked how many grams of hydrogen sulfide, since it's in the gas phase, are needed to completely react with 5.5 moles of oxygen. So in this case, we're going from moles of oxygen, and our end goal is the grams of hydrogen sulfide. So what is our intermediate unit? What is our stepping stone? Moles, and more specifically, moles of hydrogen sulfide. And to complete this mole-to-mole conversion, we'll use our chemical equation. So starting with 5.5 moles of oxygen, let's first input our stoichiometric ratio. So how many moles of hydrogen sulfide are required to react with how many moles of oxygen? What is our mole-to-mole ratio? We need 1 mole of hydrogen sulfide per every 2 moles of oxygen. Wonderful. For our next step, we need to convert between the moles of hydrogen sulfide and the grams, keeping in mind the molar mass of hydrogen sulfide is 1 gram per mole times 2 for hydrogen, plus 32.0 gram per mole times 1 for sulfur. That gives us 34 gram per mole of hydrogen sulfide, which we use to convert from the moles of hydrogen sulfide to the grams. As we see, moles of oxygen cancels, moles of hydrogen sulfide cancels, and punching it into our calculator, 5.5 divided by 2 times 34 gives us 94 grams of hydrogen sulfide. Notice 2 sig figs in, 2 sig figs out. Does that make sense to everyone? Does that idea make sense? Does this process make sense? Okay, so now let's bridge the gap even further and let's add another step. So we're asked how many grams of sulfuric acid are produced by complete reaction of 10 grams of hydrogen sulfide. So we're asked to go from the grams of hydrogen sulfide to the grams of sulfuric acid. And how do we relate these two masses? How can we relate the quantities of each species in a chemical equation? What units do we need to go through? What units do we need to go through? What units do we need to go through if we're dealing with stoichiometry?
We need to use the mole of H2SO4.
Yep, so we're going to need to go through units of moles. Exactly right. And we can utilize our chemical equation to relate the quantities of moles of each species in our chemical equation. That's really important. You always want to go to moles when you're dealing with stoichiometry, because that is the only way that you can utilize your chemical equation to relate the quantities of each species. Okay, so now that we have our solution map established, we just have to execute on this. So if we have 10.0 grams of hydrogen sulfide, we can go from grams of hydrogen sulfide to the moles of hydrogen sulfide using our molar mass. We know we have 1 mole of hydrogen sulfide for every 34 grams. Wonderful. Okay, now that we're in units of moles, we can go from the moles of hydrogen sulfide to the moles of sulfuric acid. So how many moles of sulfuric acid do we make per mole of hydrogen sulfide consumed? What's our mole-to-mole ratio?
1 to 1.
1 to 1, exactly right. Okay. So we have 1 mole of sulfuric acid produced per 1 mole of hydrogen sulfide consumed. finally, we're going to go from the moles of sulfuric acid to the grams of sulfuric acid. And showcasing that molar mass calculation, we have 1 gram per mole times 2 for hydrogen plus 32.
Scroll up
Can't
just
see.
Sorry, what?
Can you scroll up just a little bit?
This way?
Oh, I'm sorry, down.
Okay, perfect. Sorry about that. Okay.
Great, thank you.
So we have 1 gram per mole times 2 for hydrogen. We have 32 gram per mole times 1 for sulfur. And we have 16 gram per mole times 4 for oxygen. Adding this together, that gives us a molar mass of 98 grams per mole of sulfuric acid. And we use that to complete this unit conversion. And that gives us the grams of sulfuric acid produced. Grams of hydrogen sulfide cancels, moles of hydrogen sulfide cancels, moles of sulfuric acid cancels, and we're left with grams of sulfuric acid. So we punch in 10 divided by 34 times 1 times 98, and that gives us a final mass of 28.8 grams of sulfuric acid. Does this example make sense?
Professor, how did we get from the grams to moles in the first?
To get from
endpoint?
grams to moles, we just use our molar mass, or otherwise known as the molecular weight.
Okay.
Does that make sense? So like, for example, for hydrogen sulfide, to go from grams of hydrogen sulfide to moles, we use the molar mass of hydrogen sulfide.
Okay, so then we're going to be multiplying that, and then that. Okay, I see that. Sorry, I got a little lost there.
No problem at all. Really don't be shy to ask questions, and I'd be happy to answer them. And the way to know whether you multiply or divide by the molar mass is you look at the units. So in this case, if we want to go from grams to moles, we divide by the molar mass, so our units of moles end up on top. To go from moles to grams at the end of this problem, we multiply by our molar mass, so that way units of grams end up on top. Does that make sense?
Yes, thank you.
Perfect. Okay. So let's look at the following example. And the first thing that I want everyone to do is to take this equation, and what's the first thing that we have to do whenever we're dealing with a stoichiometry problem? What's the first thing that we have to do?
You need to balance it.
Yes, you need to balance the equation. So once you balance the equation, I'd like you to use the balanced equation shown above here with incomplete coefficients. You'll need to put the correct balanced coefficients and then utilize your balanced equation to complete the following 2 stoichiometry problems. So let's spend about 5 to 6 minutes on this example, and then we'll come together as a group to discuss. And if you have any questions, don't be shy to ask in the chat. And you can also help start the class off, well, as we work through this problem, by sharing your balanced chemical reaction coefficients. And if you have any questions, don't be shy to unmute and ask your question. We already see students are writing their proposed balanced equation in the chat. So here are the student proposed balanced equation coefficients. And we can use these balanced equation coefficients to then complete stoichiometry calculations. And don't be shy to submit your questions or proposed responses in the chat for these two stoichiometry calculations. And then we'll discuss in about another 4 to 5 minutes.
Professor,
Yes,
for the finding the molar mass for chlorine, because it's diatomic, we need to do 35 times 2.
yes, exactly right.
Got it. Thank you.
So let's keep working through these problems, and don't be shy to submit your proposed responses for these two stoichiometric conversion questions into the chat. And we're already starting to see the first set of student proposals, and we'll discuss these examples in about 3 to 4 minutes. Let's try to collect a pool of student responses, and then we'll discuss this question together as a group. Focus on taking these problems to a complete final answer and then proposing your solution. And then we can go through the process of revising the solution as we work through these problems together as a class. But for now, let's give our first attempt at these problems. Don't be shy to share your responses in the chat, and don't necessarily be shy to disagree with your classmates. A variety of different opinions and, whoops, sorry, this coefficient should be a 2. Looking at the chat. There we go, perfect. So it's good to see that students have provided multiple responses in the chat and have revised their responses for the balanced equation coefficients. And the responses I'm seeing in the chat look reasonable so far. Let's keep working through these problems, and then we'll discuss in about another 3 to 4 minutes. And if there are any questions as we work through these examples, don't be shy to ask them in the chat. I'd like to see responses for both parts of this stoichiometric conversion problem. And then we'll discuss in about another 2.5 to 3 minutes. And we'll discuss this example momentarily in about 2 minutes. It's great to see that students are working through both parts of this stoichiometric conversion question. And it's great to see that we have a reasonable consensus between each of the student responses that we've seen so far. We'll discuss this example in about another minute and a half as we give students a little bit more time to compose and submit their responses, or compose or submit their questions. And we'll discuss in about another minute. Don't be shy to submit your additional responses, and I'd be happy to provide feedback. Okay, so let's discuss. The class did a wonderful job balancing this equation. And now that we have our balanced equation, we're asked to figure out how many grams of aluminum are needed to completely react with 70 grams of chlorine. Okay, so we're starting off with the grams of chlorine, and our end goal is the grams of aluminum. What units do we need to convert to in order to utilize our chemical equation? What units do we need to convert to?
Moles.
Moles, yep. So we're going to go from grams of chlorine to moles of chlorine, and then moles of chlorine to moles of aluminum. So once we have this scheme in place, starting off with our 70.0 grams of chlorine, we know from our molar mass that the molar mass of chlorine, we have 35.5 gram per mole times 2. That gives us 71 gram per mole of chlorine. So we know in 1 mole of chlorine, we have 71.0 grams. Now, from our chemical equation, to go from the moles of chlorine to the moles of aluminum, we see we have 2 moles of aluminum per every 3 moles of chlorine. We got that from our stoichiometric ratio. Finally, to go from moles of aluminum to grams of aluminum, we use our molar mass. And we know that we have 27 grams of aluminum per every 1 mole of aluminum. Does this setup make sense? Does this setup make sense to everyone?
Yes.
Okay, so we're going to punch in our initial mass, which is 70, divided by our molar mass, which is 71, times 2 divided by 3 for our stoichiometric ratio, and then times 27. And that gives us a final mass of 17.7 grams of aluminum. Does this example make sense to everyone? Does this make sense to everyone?
Yes.
Perfect. Okay, let's keep going now. And let's look at the next part of this question. In this case, we're asked to determine how many grams of aluminum chloride are produced by complete reaction of 81 grams of aluminum. So we're going from the grams of aluminum and we're ending with the grams of aluminum chloride. Again, we'll be going through moles as that's the only way for us to utilize our chemical equation. So starting with 81 grams of aluminum, we know from the molar mass that we have in 1 mole of aluminum, we have 27.0 grams of aluminum. Now, using our chemical equation stoichiometry, what is the ratio between aluminum chloride and aluminum? What is our mole to mole ratio between aluminum chloride and aluminum?
It was 2 to 2.
2 to 2, exactly right. So then we see we have 2 moles of aluminum chloride per every 2 moles of aluminum. Perfect. The moles of aluminum cancels. And now to finish off this problem, we're going to need to go from the moles of aluminum chloride to the grams. And we know for aluminum chloride, we have 27.0 gram per mole times 1 plus 35.5 gram per mole times 3 for the 3 chlorines. That gives us 35.5 times 3 plus 27, which gives us a molar mass of 133.5 gram per mole of aluminum chloride. So we know that we have 133.5 grams in every 1 mole of aluminum chloride. Okay, so punching this into our calculator, we have 81 over 27 times 133.5, which gives us a final mass of aluminum chloride of 4.0 times 10 to the second grams of aluminum chloride. Does everyone have an idea of why I'm writing this mass in such an odd way? Why did I write my mass in this way?
Because it has 2 sig at the beginning.
Exactly
You
right.
want to show that.
Exactly right. We want to make sure our significant figures are conserved. So rather than writing 400, we write it as 4.0 times 10 to the second. Does this example make sense to everyone? This is the level of difficulty that you'd see on a typical exam or chapter 5 quiz question.
The 2 sig figs comes from 81 grams.
Yes.
Okay.
The input. Yeah. Since all of these operations are multiplication, you only have to concern yourself with the sig figs in your input. That's the nice thing about stoichiometric conversions.
Professor, and you got that by multiplying the 81 with the 27.0?
So we take 81, then we divide by 27, then we multiply by 2 and divide by 2, and then we multiply by 133.5, and that gives us a final output of 400 that we write as 4.0 times 10 to the second. Does that make sense?
Yes, thank you.
Perfect. So this is a great stopping point for today.